My name's Oliver Zajonc. I'm a PhD candidate at KU Leuven. I'm presenting on FHE for multiple parties using NTRU and LWE. And this is based on a pair of joint works with Jung Park, Robin Jadul, and Barry van Leeuwen. I'm being helped today by my slides. Say hello, slides. All right, thank you. So we should probably place this work and say, where are we? Okay, slides, that's not quite what I meant. I meant in the research. No, it's fine. Could you? Okay, that's better. So these are the two works we're talking about. We have a multi-key FHE scheme and a multi-party FHE scheme, and these are both based on final. As a warm-up, we should cover LWE for those of you who stumbled into an FHE presentation without knowing what LWE is. We take a key, which is a string of bits. We take a public value, which is a string of field elements. We take some small noise, and then we encrypt a ciphertext by dot producting our public noise and our key, adding our message, and adding our tiny bit of noise at the end. Now, to kind of demonstrate the main problem with FHE research, which is this kind of noise management, we're going to use the totally not patented noisometer. So let's check in on how this looks for LWE, which, it looks pretty good. The moon is far away. It's pretty safe. So let's go to the beginning and we can explain where we are at from there. So we start with final, which I suppose is the starting point for this work, because we take final, which is a single key FHE scheme based on NTRU and LWE, and we expand that to allow multiple parties to participate in the computation. But that's maybe not quite far enough back. So slides, could you take us a little farther back? Okay, that's slightly too far back. Let's go a little bit farther forward. Okay, that's better. So NTRU, as some of you may or may not know, was originally a public key crypto system developed in 1998. And at that point, it was in no way, shape, or form fully homomorphic, which...
Oh, we've lost Oliver. Hang on. Okay. Oliver, are you there? I can still see you in the room. Yeah, don't know what happened there, Oliver.
Disconnected for a moment. One moment, please. And we should be back.
Yeah, looks good.
Alrighty. So, as I was saying, NTRU was a ring-based public key crypto system. It was generated in about 1998, and at that point, it was in no way, shape, or form a fully homomorphic encryption scheme, which you will notice by the fact that it's over 10 years before Gentry's original scheme. Yeah, so let's cover some NTRU. About 15 years after that, in 2012, I believe, we have this work by Lopez Alt, Tromer, and Vaikunathan called On the Fly MPC. And this does not only an FHE scheme based off of NTRU, it's a multi-key FHE scheme based off of NTRU, which clearly means that we now have, an entire span of works based off of NTRU, which do, FHE, right? Okay, so that's bad. That's not great. Let's quickly pivot. We're going to quickly cover a few because, well, this is, I think, the real beginning of where our work starts. So this is about 2015. It's an entirely LWE-based single key FHE scheme. And they introduce a thing called, okay, slides, lunch was 2 hours ago. Let's try that again. Okay, that's better. We take the homomorphic accumulator, which is a nice thing. Did I lose connection or did somebody just join?
No, you're still with us.
All right, cool. Noises in my ears. Excellent. So we have the homomorphic accumulator, which is a set of 4 algorithms, which they define later on in the work, but we don't care about the actual definitions. We have the encryption scheme, some nebulous, possibly LWE, possibly not encryption scheme. We have a way to initialize, we have some incrementation, and then we have a way to extract at the end. And the way that looks in practice is we take our input, we chop it into tiny bits. We take the first bit as our initialization. Then for each subsequent bit, we encrypt that and add it on in some way using whatever our increment turns out to be. And then we use this extraction method. And at the end, we should get, if everything's defined nicely, an LWE encryption of our input. This isn't 100% correct. I am skipping over a lot of details, but for the purposes of this talk, basically correct. Now, this looks a lot like a bootstrapping, and in fact, it does turn into a bootstrapping. So you generate some keys, which are encryptions of a partial decryption. You initialize using your ciphertext, and you loop over all of your public noise, and you start incrementing with this public decryption, or this partial decryption. And at the end, you should get, after your extraction, you should get an LWE encryption of your original value. So you have a nice little bootstrapping here. Now let's move over to final. And they define an NTRU-based scheme, which looks a lot like GSW. They define NGS, an NTRU-based GSW-like scheme. The keys here are polynomials. You also have some noise, which is a small polynomial. And then you have your encryption, where you divide your noise by your key, and you just add your message onto the end. Decryption here would be relatively simple. You multiply by your key. You divide by this delta value. You round away, so you remove this noise term entirely, and then you can divide by your key again, and you get your message. Now you notice that this doesn't say encryption, it says senc, which is scalar encryption, because we also have a vector encryption. This does basically the same thing, except that your noise is now a vector of polynomials. The reason we need both of those we'll get to in just a second, but let's quickly check in on how our noise looks, because we did have those attacks earlier on NGS, which does limit how much noise we can handle. So let's just check in on the noisometer. Okay, that's a little bigger, but we're still fine. So now back to why we need both scalar and vector encryptions, and that's because we have this nice thing called the external product. It lets us perform a multiplication or a homomorphic multiplication, but it does take a scalar encryption and a vector encryption. So we can't do it with two vectors and we can't do it with two scalars. This does make it very nice because it doesn't generate a lot of noise. Let's quickly check in on that. Yeah, still nice and small. We're pretty good. So I'm missing something still to get the homomorphic accumulator. Yeah, thank you, slides. It's the bootstrapping keys. These aren't the most interesting thing in the world here, but we are going to mention them because they will become important later. These are vector encryptions. They're vector encryptions of not just the polynomial, not just the partial decryption, but actually of a polynomial where the power is this partial decryption. And the reason for that is because we're going to need to use this external product as our increment, which is a multiplication. But for LWE decryption, we actually need addition or subtraction. So we start with we initialize this way. We now can external product with these keys that we just defined, which remember are NGS encryptions. And at the end, we have a scalar encryption of essentially an LWE decryption in the power of a polynomial. Now we do have to get from an encryption of a power of a polynomial to just the actual decryption. This is done by a relatively technical thing. We multiply by this monstrosity of a polynomial. This does work. You're going to have to trust me on this or read the paper, one of the two. And then we just have to get back to LWE. Now, key switching from NTRU to LWE is relatively simple. The real thing you need is this key switching key, which is roughly an LWE encryption under the LWE key of the NGS key. Right? So this will become important later. So now we need to get to multiple people, right? And if you've seen FHE for more than one person, you'll have seen the terms multikey and multiparty, and we will be covering both. So let's just go over what we mean when we say multiparty. Okay, not quite. Let's try that again. Okay, that's better. So the main difference between multikey and multiparty is multiparty has communication between the parties as part of the setup, and multikey generally does not. So for a multi-key, everybody will encrypt their thing, send it to the server, and forget about its existence. And for multi-party, everybody has to do some MPC together, unfortunately. So let's take the naive approach here. We generate a communal secret key. We output this to all of the parties, and we generate the bootstrapping keys that we need, and we send that to the server. And this does present a slight security problem. The server can collude with any one of the parties to learn anybody else's inputs, because the server receives the inputs. They can send that to any other party, and all of them know the same key. So this kind of defeats privacy a little bit. So instead what we do is we generate a communal secret key, and we never reveal it. We now generate the bootstrapping keys, which remain the same. We send those to the server, all good. And we generate key switching keys from everybody's individual private key to this communal secret key. And we also generate key switching keys to a multi-key version for decryption. What you can also do is say, well, we just decrypt using MPC again. That's also fine. But the main thing here is, well, we get multiple party FHE, and the extra bit of MPC at the front is the only extra cost. And you only have to do this once, and then you can do your computation at the same cost as single key FHE. And you also prevent collusion between these players and the server, which is nice. Okay, slides, I get that you're antisocial. I don't like talking to people also, but we will cover multi-key just so that you don't have to talk to people, all right? Okay, multi-key FHE. So for this, we do need a form of FHE, or an encryption scheme, that accepts multiple keys. For LWE, the way this works is encryption remains roughly the same, except that each party gets their public key space in a vector. So your ciphertext does grow a little bit, but it lets you just do decryption the normal way, and everything kind of works out. Now, let's quickly check on our noisometer. Yeah, this is the same as single key LWE, roughly. It's pretty fine. Now let's check on multi-key NGS. Now this is actually secretly the same. The encryption is the same. It looks the same. We can, in fact, we do have to check on how we get multiple keys, and that's actually really easy. Let's say we add two scalar encryptions together, and they each have a different key. Well, we can actually write this as an NGS encryption under one key, where this one key is the product of the two keys. Now, there is a slight problem here, which is that our noise, you'll notice, is now a product of polynomials, which grows very rapidly. This is really kind of bad. As you can see with the noisometer, that moon is getting very large and very scary. It is still mostly fine. We can work like this, but this will be a point of worry later. Now, here's the real problem. Remember those key switching keys from earlier. We do need to get back from NGS to LWE. Well, now we need an LWE encryption of our NGS key. But our NGS key is now a product of secret keys, which we can't, just reveal. So we could, we are doing FHE, right? We could just have everybody encrypt their own NGS key and just multiply the ciphertext together. That should be, that should be fine, right? Let's check the noisometer. Let's see how that works. Okay, that's bad. Okay, slides, I'm not screwed. Otherwise, we wouldn't be here. This paper did get published, and the reviewers weren't, they did look at the paper. So we can do this via a nice construction called the hybrid product. Slides, I said the hybrid product. Okay, slides, what's wrong? Okay, I get that you don't want it. What? Can you tell me why? Okay, it is very technical and boring, but we do have to kind of cover the hybrid product. It's not our work, but it is a nice construction. It does things. Can you at least show the lemma that says the hybrid product is a useful construction? Okay, thank you, slides. So as the slides mentioned, we will not cover the hybrid product in detail, but we are going to cover what it does exactly. So the lemma kind of goes like this. We take a multi-key RLWE encryption, and we leave the last number of spaces blank. These are all zeros. And we run this through the hybrid product, and a key thing to note is the hybrid product keys here in the middle. These are generated by party I, and they can be generated independently by party I, so they don't need any computation or MPC between the parties. Like there's no communication there. And we get out an RLWE encryption with one extra slot filled. It's no longer CI -1, it's now CI. And we actually get an RLWE encryption of whatever our previous message was multiplied by the next NGS key, which is really nice. So we can now just start with 1 and a pile of zeros, hybrid product for each of the parties, and at the end, we get our key switching key, which is actually great. This generates, we can do this without bootstrapping. It generates way less noise. Let's check on the noisometer. Okay, it is very close, but this is fine. We can actually check that it's fine. We're going to quickly look at what our noise limits actually say now. So this first, we're going to do this by LWE degree. And you noticed in the NGS, our noise was a product of polynomials, and the number of polynomials is actually determined by how many parties you have. So if you have more parties, then your noise goes way up. This first LWE degree is the one, or is close enough to the one used in single key final, and we can support 2 parties there. So we are multi-party. This does count. And if we, double it, then we get 4 parties, and so on. This is more of a proof of concept than anything else. This is terabytes of key data over here. Cannot possibly recommend that as anything practical. However, we do have some improvements here. So these are, the top 2 here are TFHE-based multi-key schemes. These 2 are other NGS-based bootstrappings for multi-key. And the main thing here is we're not outrageous with key material. The other 2 NGS ones have better key material, but we get asymptotically better numbers of polynomial multiplications in our bootstrapping. So everything else needs is quadratic in the number of players, and we are actually linear, which is, very nice. And that's actually all I have for you today. If you have any questions, now is the time.